Okay. Did you hear me? Is there anybody?
Yes, Professor, we can hear you.
Okay, okay. So we will have the session of the afternoon, and let me thank Professor Anna Maria Pau for giving her seminar today. And just to briefly introduce her, I wish to remember that Anna Maria Pau has the degree in civil engineering, got at the University of Cagliari, and the PhD degree in structural engineering from Sapienza, University of Rome. She is now associate professor of structural and solid mechanics at the Department of Structural and Geotechnical Engineering of University La Sapienza. And her research interests include multiscale, of course, modeling of complex materials, wave propagation structures, non-destructive evaluation, and structural health monitoring, and many other topics. And please, Professor Pau, start your presentation now. Thank you again.
Okay, thank you, Patrizia, for your introduction, and thank you for having invited me to do this seminar. I am not sure I can hear you, but I hope that everything's fine. Okay, I'm sharing my screen. Okay. a minute. So stop the video right here. And so they are not seeing. Okay. Share screen.
And after that, start.
I was already in the presentation. Like this one. So I'm supposed to start again. Experimentally, one
Excuse me, Professor,
and,
we cannot hear you.
You cannot hear me.
No.
They cannot hear me. Here, nothing is working. My computer is completely stuck. No.
Now we can hear you.
Come Qua niente.
Okay. What's this?
No, the first one.
Okay.
Can you hear me, guys?
Yes, yes. It's okay now.
All right. Am I supposed to start again? Yes, from the beginning. Because we are recording right now. Okay, all right. So this presentation is about the modeling of the propagation of waves in composite materials by equivalent multi-field continua. Why do we do so? Because the behavior of some materials, some experimental behavior, is not anticipated by the classical continuum theory. And this is because the material of the microscale has an influence on the macroscale behavior of the whole thing. And this is typical of some kinds of materials, which can be, for instance, composite materials or phononic crystals and metamaterials. This kind of materials are man-made materials, which can generally be obtained by 3D printing, which have extreme, unexpected, and exotic properties. These are like, for instance, negative Poisson ratio, which means that if you stretch a specimen in some direction, instead of observing a contraction in the direction orthogonal to the direction in which you're stretching, you observe an expansion or opposite. If you compress the material, instead of expand transversally, it contracts transversally. Or some materials can have even zero thermal expansion when you have a change of temperature, or negative stiffness, or even frequency band gaps. Frequency band gaps are frequency band in which frequencies, some waves cannot propagate. And recently I've read a paper discussing a new printed material which has at the same time acoustic and vibration band gaps. And it seems that that's the first time that such material have been produced, because up to now I have always seen materials which were just acoustic or mechanical insulators, that then they had just acoustic or elastic band gaps. But it seems that with a particular design and optimization, it is possible to optimize the microscale of the material, and they obtain these coupled acoustic vibration band gaps at the macro scale. Other kinds of phenomena which can be observed are, for instance, the conversion of axial deformation into twists or even cloaking. Cloaking is the phenomenon by which some discontinuity is just not seen by a wave which propagates unaltered through the discontinuity, which instead in normal conditions should be reflected and observed as a sign of the presence of some discontinuity in the material. How is it possible to model this kind of phenomena? This is possible by using Kosura and second gradient theories. These theories enable the accounting for material particle micro-rotation, or the transmission of couple stress actions, or even actions at the distance. In this, the content of this presentation will be first the presentation of the elastodynamics, or in Kosura and second gradient media, and then the description of this two-scale micro-macro discrete continuum equivalence procedure, which is used to model to obtain a macro Okay. Okay. All right. So I was just willing to revise the wave propagation in Cauchy media, equation of motion, a stress-strain relationship, linear stress-strain relationship, where the strain is just the symmetric part of the gradient of displacement. Now, with some using some tensor identities, we can obtain this Navier differential equation of motion, where the unknown of the equation of motion is just the displacement field. When we are solving wave propagation problems, we search for solutions that are harmonic propagating waves, which have this form, meaning that the displacement field is some wave which propagates in time and space with some amplitude A. The amplitude is described by the vector A, and K is the wave number, which is a vector whose modulus is the opposite of the wavelength, and whose direction is the direction of wave propagation, which is orthogonal to the wavefront. And if you want to determine the conditions which have to be satisfied for a progressive wave, which means for a solution like that, to solve the equation of motion, we just have to substitute this equation in the Navier equation. In this way, we obtain this other equation, which is the equation of motion for traveling waves. Now, if we work a little bit, do a little algebra on this equation, we can write it in this simple form, where A is the acoustic tensor. And again, by working on this tensor, and well, I wanted to add that this equation of motion has a non-trivial solution if C square and A are respectively eigenvalues and eigenvectors of the acoustic tensors. Therefore, we are interested in the form of this acoustic tensor and in its eigenvalues and eigenvectors. It is possible to decompose, to write this acoustic tensor in this form. This form is called spectral decomposition of the acoustic tensor. And we have a spectral theorem which enables to the conclusion that if the tensor has this form, this quantity is just an eigenvalue, as it is also an eigenvalue this quantity. And in fact, these two quantities correspond. The first one to longitudinal waves, which have displacements occurring in the same direction as the direction of wave propagation. These are longitudinal waves. And while we have other two eigenvectors, which are orthogonal to the direction of the wave propagation, meaning that they are contained in the plane which contains the wavefront. And in this case, displacements are orthogonal to the direction of wave propagation. This scalar product is just null. These are shear waves, while these ones are longitudinal waves. And a variety of terminology exists for these two types of waves. For instance, longitudinal waves are also called dilatational, irrotational pressure, and primary waves. And transverse waves are called shear, equivoluminal, distortional, and secondary waves. It is interesting to observe that in a homogeneous and isotropic solid, the wave velocity does not depend on the direction of propagation, neither on the frequency of the waves. All these waves in a Cauchy medium are just non-dispersive. Non-dispersive means, as I said, that the wave propagation does not depend on frequency, and this has a consequence. The consequence is that a given disturbance doesn't change its shape while it propagates in the medium. This is an example of a non-dispersive wave. You see that we have a simple disturbance, which is not altered by its propagation in space. This is the case instead of dispersive waves. We have an initial disturbance which changes its shapes while it propagates in space. And this change, these different properties depend on the fact, in the first case, that the wave propagation, the propagation velocity, the phase velocity does not depend on the frequency, while in the second case, this wave propagation velocity depends on the frequency of the wave. Actually, and experimentally, often these dispersive characters of waves is observed. Actually, and experimentally, often the continuum is not able to represent these dispersive characters. One solution can be use the Kosura medium. The difference between the Kosura medium and the Cauchy medium is that, differently from the Cauchy medium, where this limit is null, in this case, two surfaces can exchange with each other also couple stresses, which are couples per unit surface. Therefore, in a Kosura medium, they two surfaces exchange with each other either stresses and couple stresses. And beside this, a Kosura medium is endowed with displacement and rotational degrees of freedom. Each point, the configuration of each point is described not only by its displacement, but also by three rotations. And these rotations can be either collected into a rotation vector or be expressed by in matrix form. And there is obviously a relationship between the rotation matrix and the rotation vector, meaning that the rotation vector is the axial vector of the rotation matrix. I also wrote here some balance equations for the Kosura medium, showing how it is possible to obtain the balance equations for an infinitesimal element. You see here, I have reported the tension stress, which are the same as the Cauchy one, besides the fact that the Kosura medium, this tensor is non-symmetric. And here I have reported the couple stresses. Now, if you write down, for instance, the balance, the rotational balance about the axis x sub 3, you can obtain this equation. You see that in the absence of couple stresses, this part cancels, and you just obtain a symmetry, some symmetry properties for the stress tensor, which is the situation which occurs in a Cauchy medium. While on the contrary, in a Kosura medium, you come up with this further equation. Therefore, you have 3 translation balance equations plus 3 rotation balance equations. Here, you can find this equation written in different ways, because I have used here the axial vector of the anti-symmetric part of the stress tensor. There is a stress in the case of a homogeneous and isotropic Kosura medium. There is this stress-strain relationship, and the strain displacement relationships are this one. This is the corresponding of the Cauchy strain tensor, besides the fact that this is non-symmetric, plus here we have the gradient of rotations, which is something similar. It's like a curvature-like. That's why I've used the case symbol. It's a curvature-like strains, and something similar to the curvature. And in the end, if we substitute the stress and strain relationship and the strain displacement relationship in the equations of motion, we come up with these Navier differential equations of motion, where you see we have some additional terms in respect to the Cauchy terms. For instance, we have these other constitutive constants, plus we have the discoupling terms. Therefore, you see that even the rotation vectors appears in the translation balance, and the displacement vector, the curl of the displacement vectors appears in the rotation balance. Therefore, we have this coupled equations, coupled displacement rotations field. I'm not going too much into this, but you can find in books this rotation balance written in this way or in this way. This is because this coupled stress can be written either as a matrix or as a third order tensor. That's a choice you can you have to do, yes, when you write down the equations. And we do the same with the Kosura medium. That is, we search for solutions that are harmonic progressive waves. Here we have a part of the solution we are searching for, which has the same form as we assumed it before. But we have also to make some assumption for the rotation field. And in general, we search for monochromatic waves, meaning that we assume that all the frequency is given. Frequency is given for both the displacement and rotation components. And we want to determine the conditions which have to be satisfied for a monochromatic progressive wave to solve the equations of motion. The equations of motion are these ones. We substitute this solution in the equations of motion, and we come up with these equations of motion for progressive waves, for monochromatic progressive waves. Just working a little bit on this equation, we can extract the acoustic tensor. The acoustic tensor has this form. I'd like to let you know that I've been working on these expressions in during the last month, because it's you cannot find these equations in books. You can find the solutions. The solutions are well known, but this form in terms of spectral decomposition is not, I mean, it's, I don't like to say it's new, but it's kind of a recent, something I did recently, but I couldn't find it in books. I couldn't find in books these compact expressions. You can find some things expressed by components, very with a lot of terms, but nothing so compact and visually appealing. Can I say that? Yes, let's say appealing. So spectral decomposition, what does it say? It says that we have some waves which have just components along the direction of propagation. And these are the roots of this tensor. Here there is a mistake. Sorry about that. I have to correct that. Anyways, these two waves are, one is a longitudinal wave, which is the same as the Cauchy one. And this is a wave which has displacements only in the direction of wave propagation and no rotation. The amplitude of the rotation vector is just 0. And we have another wave, which is a longitudinal torsion wave, which is a wave which has no displacement and just one rotation according to the direction of wave propagation. The point is that the interesting point is that while this wave is non-dispersive, the same as the Cauchy medium, this other wave, although this is not, there is a mistake here. This is actually minus omega times j divided by beta plus 2 eta. This should be the denominator. And this is a omega square. This is for alpha. There is an omega square somewhere. Yes, here. There is somewhere at an omega square at the denominator. But the point is that this longitudinal wave is dispersive. Okay, so let us give a look at this other part of the acoustic tensor. You see that here we have these two vectors, I minus n tensor n times A, and vector product n times B, which are both orthogonal to the direction of propagation, which coincides with n. Therefore, if this one is the direction of propagation, this is a given amplitude vector, this tensor product is the longitudinal wave, while these other waves have displacements contained in the plane orthogonal to the direction of propagation. That is, they have displacement contained within the plane which contains the wavefront. And their speed can be calculated by searching for the values of wave number, which make known the determinant of this matrix. And all these waves, if you give a look at the displacement field, they are all shear waves, meaning that they have components orthogonal to the displacement field. Plus, they have rotation about axes which are contained in this blue plane. And we have, in the end, and they are also both dispersive. Then we have one longitudinal wave. This is a dispersion diagram. If you're not familiar with dispersion diagram, a dispersion diagram is a diagram which shows the wave number as a function of frequency, or in terms of phase velocity of group velocity, the phase velocity or the group velocity as a function of frequency. If you show the wave number as a function of frequency, you can tell whether a wave is dispersive or non-dispersive, because a non-dispersive wave has a dispersion diagram which is simply a line. Therefore, we say that longitudinal waves are this red line, and they are just non-dispersive. While torsional waves, as I told you before, torsional longitudinal waves, which are this blue line, they are dispersive. Not only they are dispersive, they have a band gap, meaning that for frequency smaller than 100 hertz for this material, they cannot propagate. This is a band gap for torsion waves. The other waves are these mixed transverse rotational waves, which are both dispersive. This one is almost a line. When I'll show you the diagram showing the wave propagation, you see that that's not exactly a constant wave propagation velocity. And this other one is a mixed transverse rotational wave, which is a sort of bending shear wave. While this other one, this purple wave is sort of shear rotational wave, where the rotation occurs in people in the room will okay. I have to interpret the wave. So the purple one is this wave, while the black one is this wave. Therefore, there is a sort of bending like, and the other is a sort of torsion shear. It's well, for those who are in person, they have experience and an interpretation of the wave. Sorry for you guys who are not here. And the phase speed has this form. Again, longitudinal wave, constant speed, no dispersion. Purple waves, shear torsion, small dispersion, almost constant, strongly dispersive. This other torsional and mixed transverse rotation wave, like those bending like waves. You see here all this area for frequencies smaller than 1000 Hertz, no propagation, meaning that there is this band gap. Okay, now that I've told you all this story about the Cauchy continuum, it's going to be easier to present how wave propagate in the second gradient medium. Basically, the second gradient medium, in the second gradient medium, we have just a displacement field. The point is that while the displacement of one particle is described by just 3 displacement components, the strains are instead described by either the strain tensor, meaning like the symmetric part of the gradient of displacement, plus a second gradient tensor, which is a curvature-like tensor. Here we have a stress tensor, which is basically the same as the Cauchy, plus we have a hyperstress tensor. This hyperstress tensor is a third-order tensor, which can be, which is basically a matrix of matrices, which has 3 subscripts, as you hear. And I made a drawing here to give you a sense of what is this hyperstress. Basically, each term of this hyperstress tensor represents a couple of forces. This couple of forces acts along the direction k. This is ijk. K indicates the direction, and they are orthogonal to the plane of normal j, and they have a lever arm in the direction I. And I have drawn here all the forces acting along direction y. Therefore, you have all the terms of the third order tensor, which are ij1. If you try to write down the equation of motion for this, for the infinitesimal volume of a solid, for instance, just the translation balance about x sub 1, you can observe that in the translation balance, the increment of the couple of forces gives a contribution. The rotation balance gives us some symmetry relationships for the stress tensors, while we have only balance equations representing the translation balance, which are these ones, meaning that to the divergence of the stress, something adds up. And this is the divergence of the coupled stress tensor. Again, we do the same job we did before. We have some stress strain relationships, and we search for solutions which are harmonic progressive waves. And in the end, we see equations of motion and can derive the acoustic tensor. This tensor has, again, a spectral decomposition, which is this one, where we have that some eigenvalues are these ones, and these represent shear waves. And shear waves, like in the Kosura continuum, are non-dispersive. These non-dispersive waves have displacements just orthogonal to the plane, contained in the plane orthogonal to the direction of wave propagation. We have this other component, which instead represent axial waves. We have, for axial waves, meaning that the sign indicates the direction of wave propagation. And these four waves, one couple is non-dispersive, sorry, they are all dispersive. One couple is propagating, while one couple has this wave number, which is imaginary. And an imaginary wave number means that the wave cannot propagate. These are called evanescent waves. Now, in the end, for this second gradient media, this is the dispersion diagram. We have these longitudinal evanescent waves. You see that here there's the imaginary part of the wave number, and longitudinal propagating waves. And if we give a look at the dispersion diagram, we see that we have a non-dispersive shear waves and dispersive longitudinal waves. Now I see I have another 5 minutes. Maybe I can just leave a couple of minutes for questions. I don't know. Are there any questions up to now? Okay, so another couple of minutes. Okay, so basically you have seen how waves propagates in this Kosura and second gradient continuum. Therefore, if you see something, some experiment, if you observe some experimental behavior and observe, for instance, that a longitudinal wave is dispersive, you can say, okay, that must be a second order effect, second gradient effect. Or on the contrary, if you observe a torsion wave, you can say, okay, that's a rotational effect that can be described by a Kosura continuum. And this can give you a hint on how you could lead an identification of a continuum equivalent to a micromodel. This is generally done by a multiscale approach. This is in mechanics, it is generally sufficient to act only on two scales, a micro scale and a macro scale. And this is an approach, as also Professor Trovalucci showed in her first lecture, which was introduced by Voigt in the 19th century. We did not invent that, but it's based on a mean work equivalence between a representative volume element at the micro scale to the work density of the stress actions at the macro scale. This is a process, a procedure, size, shape, a zero or of a mix, even spanning several orders of magnitude, despite the fact that in this case, this is done only on two scale. And, okay, how is it done? It's based on the observation kinematics at the micro scale. For instance, it is possible
I think we have a problem with connection.
Yeah, I'm connected to the Sapienza network. It is not, unfortunately, it's Sapienza. Okay, can you hear me now?
Yes?
Or
No.
right?
No, the connection is really bad.
The relative length of contact point and the relative rotations between particles. You define the forces that particles exchange with each other. And in this case, they can exchange forces. And you write down the virtual work of the contact actions, which is the sum of all the work done for by these forces. And obviously, if you analyze the dynamics, you have to write down, to add also the work done by inertia forces and the moments of inertia. And at this point, you have to introduce a map relating discrete to continuous kinematical fields. This can be done by a Taylor expansion of the vector fields. And as soon as you substitute this equation in the expression of motion, you will be able to identify the components of the stress tensors, because these come up naturally. And according to the kind of map you chose, you automatically identify a Kosura, a second gradient, or a Cauchy continuum. We did so for the case of a microporous composite material, which is something which has this form. It's a mixture of rigid grains embedded in a ductile polymer matrix, which can be in principle contain micropores or micro cracks. And here you have different, you can see different lattices interacting. This lattice, this red one, represents the interaction particle-particle, or this one, this blue one, represents the slit-slit interaction, and this green one represents the particle-slit interactions. You do basically the same as I showed you before. You have some kinematical description for the fine discrete model, which are the displacements of the brains, the rotations of the brains, and the displacements of the slit. You define some strain measures of this discrete assembly, and then define interactions between particles, slits, and particle slits. You write down the mean virtual work, you introduce a kinematical map, and in the end, you come up with some expressions of the stress tensors, which in this case were formulated for a linear case, although there is no restriction whatsoever, meaning that if you introduce the appropriate stress-strain relationship in here for these contact actions, you could be, in principle, also model some nonlinear phenomena. We have analyzed the case of a one-dimensional microcracked one-dimensional bar, and that's a static problem. We have a one-dimensional bar fixed at one end, and this is a static problem. We have just a static force acting on the free end of the structure. And we did all these calculations and even made a comparison with a finite element model, considering different densities of different core densities. And this is on the right, the comparison which we obtained for when considering the interaction between particle and slit. The dots are the finite element model results, while the lines are the real results obtained with the equivalent model. And you see that there is practically a superposition with the two models. And this is due to some kinematical hypothesis we did on the stiffnesses of the connections between, this is due to some hypothesis on the form of these forces representing interactions between the different components. We did also some experiments on wave propagation and calculated the dispersion diagrams. And what we obtained was the fact that there are some, I'm almost done, some propagation modes which involve, which are basically the modes of the pores, and some other propagation modes which are basically modes of the matrix. And the case is this red line. There is a mistake here. It's actually omega over kappa. This one, sorry, is like my battery is down almost. This is a propagation modes of the pores. I was saying this green line represents the dispersion curve for a uncracked bar, and you see the difference between the blue line and the green line occurs for the difference in wave propagation for the matrix, for the cracked and uncracked matrix. And this propagation mode, involving all the pores, is actually very sensitive to a change in porosity. But some doubt came, to my mind, and I told myself, does this mode involving only the pores actually exist, or is it something which is only in my mind? Then I made a finite element model, and my surprise, I found that you see here, there is a mode, a propagation mode, which includes basically the matrix. And here there is a tail of a mode which includes the pores. Therefore, this will require further investigation, but it's probably actually true, because I didn't say anything to the finite element model. This is just a simple plane strain finite element model. And yes, actually it exists, and it's also probably very sensitive to the pore density, which may be an interesting characteristic if one wants to gather information about the porosity of a material by observing the speed as is done for the material characterization. For instance, take isotropic materials. You can characterize constitutive by propagation velocity. There are methods to and presentation, and I wish to thank you all for listening, and I'm here to answer your question if I can, and if you have some, and yes, that's it. I don't think they see you because I have to turn on the camera. Everything is stuck.
Okay. Your screen is also shared, but maybe they can listen me. Can you hear me?
Yes, I can hear you and you can see me.
E qui appare questo adesso. Che cosa sono le gole dell'Alcantara?
Non ho idea.
È tutta questa roccia scistosa, sembrano le gole dell'Alcantara. Va bene. Could you hear me? Please send me a feedback as I cannot see anything.
Yes, yes, we can hear you. Yes.
Yes, we can hear you.
No, dico ai ragazzi a casa. Eh?
L'ho spento.
Oh, ecco. Ok. Quali ci sono? Thank you, Professor Pau, for your seminar, and I hope that she clarify some further aspects of applications of multi-field continua. And we are a little bit over with the time, and I need that we need a short break for rest. And before inviting Dr. Fantuzzi, I think that we can stop for 10 minutes, start at 20 minutes past 4. Then we will collect your answers. Who has get a master's degree at the University in Civil Engineering at the University of Bologna, and then the PhD in Structural Engineering and Hydraulics at the same university. And he, maybe some of you remember him because he held for two editions a course on modeling of offshore structures within our PhD program. And he has a very important editorial activity. He's a guest editor of many special issues and reviewer for hundreds of journals in the international journals, and also writers, authors of more than 100 papers in international journals. His research focuses, of course, in mechanics of solids and structures, fracture mechanics, implementation of numerical methods for design of structure, application for composite materials, and in particular in offshore engineering, and some specific numerical methods as quadrature method, mesh-free elements method. And today he will give a lecture that is focused also on the applications of a particular kind of non-local continua that we classified and named as micropolar continua. And I wish to thank him for accepting our invitation, and please, Nicholas. Il ragazzo non è via?
Sì, sì, vediamo. Beh, me lo posso aprire, ok. Ok.
He will amaze with the special effects
No.
of Kosura materials.
No effects, only slides.
Size effects.
Size effects.
That is the same.
Okay, hello everyone. Thank you very much, Professor Trovaluce, for the introduction. It's really a pleasure for me to be here to present this research that we are carrying on together. So as mentioned, we are discussing about material symmetries, in particular using hexagonal shaped composites. So let's see if this works. Okay. So the outline of the presentation is the following. I will give you a short introduction to micropolar theory just to introduce the notation, even though you have seen this many times during this course. Briefly, I will discuss about the modernization procedure that we are using for going from the micro model to the continuum model. And then basically all the presentation is about numerical applications and implementation of this continuum. Basically, we want to verify if, let's say, Kosura media as a significant in practice, okay? Not only a mathematical framework, and then some conclusions, of course. So first of all, we have to give, framework of application of this kind of composites. As you may know, we have several kinds. We have layered, short, or long fiber composites, which are used, for example, in aeronautics or automotive. Then we have particle-based composites or functionally graded materials. These materials are generally employed for coatings. And then you have polycrystals with thin and thick interfaces. For example, Dr. De Bellis showed you some applications with thick interfaces, considering trusses or beams. In the present case, we are focusing on thin interfaces. So the two pictures that you see over here. These kind of polycrystals are used in the industry, and here you see some examples of alumina and zirconia composites. The microstructure is, as you see from the pictures, basically hexagonal, roughly hexagonal. But this is why the research focuses on hexagonal shaped composites. The following slides will show you the micropolar model for 2D applications. So as already discussed, micropolar theory has an extra degree of freedom compared to the classical continuum mechanics, which is the micro-rotation. This micro-rotation generates a non-symmetric shear and shear strain and shear stress. And also, in order to get equilibrium of the continuum, you need curvatures and couple stresses. This, of course, goes into the energy of the model, strain energy, which is governed by a constitutive equation in which you have, we can call it classical, but actually it's not a classical constitutive matrix, because once again, we have to say that the shear, stress, and strain is not symmetric. So of course, the terms are not the same. But we have extra parameters to set up, which are indicated here as B matrix and D. So the B ones connect the normal and shear stresses to the curvatures, and of course the microcouples to the normal and shear strains. And D matrix is the matrix that relates microcouples and curvatures. And of course, with a micropolar constitutive matrix, you can assume you can obtain a Cauchy one, okay? Because Cauchy is just a subcase of micropolar theory. So let's move quickly to the microstructures that we are considering. We have, as we said, hexagonal shape microstructure. And we have parametrization, which is governed by 4 parameters. We have a relative length, which basically relates the vertical and horizontal projection of the edges of the hexagon and 3 angles. So by changing these 4 parameters, you can obtain several shapes. Just to stay, to a closer set, we defined alpha 1 equals 0 and relative length to a fixed number. So basically by changing only 2 angles, for example, we can get these 3 geometries. One is a regular hexagon. One is an hourglass shape. And one is, we call it asymmetric. Why we chose these? Because these 3 geometries, they have 3 different constitutive relations. One, we call that orthotetragonal, due to the fact that, and we will see that shortly, there are several relations in the terms of the constitutive matrix, which are very close to, we can say, isotropic material. Then the hourglass shape has auxetic properties. Auxetic, we already discussed this. Auxetic means having a negative Poisson ratio. And a chiral constitutive matrix is a matrix in which we have a coupling between stresses and curvatures or microcouples and strains, which this kind of coupling does not appear in the other 2. And of course, since we have a micropolar model, we are able to also investigate the scale of the material, something that you cannot do with Cauchy continuum. So for each geometry, we have 3 scales that we call large tiles, medium tiles, and small tiles. Regarding the modernization procedure, we are using the procedure introduced for the first time by Travalucci and Masian in 1999. The procedure is very simple. It is based on 3 steps. So the first step, you have to define the RVE, which you can see here. And of course, the procedure is based on the interactions between the particles, which can interact by normal forces and microcouples. Then each contact area between the particles needs to define a stiffness matrix, we can say, or generally stiffnesses, which are represented here. You have to define a normal stiffness, a shear stiffness, a rotational stiffness, and you can define also the latency effect of the interaction between one tile and all the other tiles. So you see an example here, you have a central tile that interacts with 6 other tiles. So for each surface, you have normal, shear, rotation, and the latency stiffness. For the following examples, most of them, they have only normal shear and rotation stiffness. I will show an application of the latency also, just to show you the effect of the latency in this kind of microstructure solids. Then basically the procedure is able to go from the RVE to a constitutive continuum. And once again, the procedure is able to identify classical, coupling, and micropolar sections of this matrix. So moving to the implementation, we are using a standard, we can say, finite element model. The model is based on a Q4 element. So 4 nodes for each element. And we are using a reduced integration scheme due to the fact that micro rotations, they have a different derivation order compared to the displacement. So according to the literature, it's better to follow this kind of scheme. Of course, you can extend this. Actually, we did it, but not published yet. Also, implementing this kind of approach for different elements and different integration schemes. You see in this slide the definition of the stiffness matrix, which of course comes from the energy, and the load vector, which comes from the potential. This is all standard, let's say. Maybe less standard is how we included the reduced integration, which is basically, it's not completely reduced, of course, it's selective integration, also called, which means we are integrating in a reduced manner the shear contributions. So in order to do so, you have to, let's say, reorder the vectors in your implementation, as we did. So we kept normal stresses and microcouples on one side and shear stresses on another side. The same for the strain. So you have to reorder once again the constitutive matrix, and this changes a little bit, the characters in our story. And this allows us to get 2 stiffness matrices, one that is integrated exactly and one reduced. So basically this is a 2x2 Gauss integration, and this follows a single point Gauss integration. Okay, saying so, you see in this slide another implementation. This, we call it the discrete model, because in order to test our continuum mechanics, we need sort of comparison. So we build discrete model, which is actually made of particles and elastic interaction, exactly as our starting micromodel. But in this case, it's a complete, say, finite element model. This was done using Python and Abacus. So Python is able to create all of that, basically, with each single tile and every interaction. So normal, shear, and rotational stiffnesses are defined. Okay, so let's go to the applications. We start with static analysis, and we also performed dynamic simulations. For the static analysis, we have a rectangular panel clamped at the bottom with 2 kind of loads: horizontal load applied in a limited area, and a top load also applied on a limited area. Why this has been done? Because if you apply the load, say, for example, here, this was proven by many, also by us, but also in other works. These kind of models, they show their peculiarities when you have discontinuities. So if the load or the boundary conditions are uniform, you don't see, say, large effects and advantages of using Kosura continuum. So for example, other applications have been done using holes. As you place a hole in the domain that is a discontinuity, so you see the Kosura effect. Okay, so let's start with a regular shape, which has an orthotetragonal constitutive matrix. As you can see from the matrix down below, as I already mentioned, we have no coupling, so B matrix is 0. The matrix A, as you see, has this component and this component the same. These 2 components relate the normal stress in X and Y direction with the normal strains, which are the same. So this means that the material has an isotropic behavior in plane, because basically the elastic modulus acts in the same way on X and Y. And also in this case, the shear, the 2 components are the same and very close to the normal values. The out of diagonal terms, they represent basically the Poisson effect. So the contraction, in this case, is positive. So this material behaves like a classical isotropic material, more or less, because we have scale effect here, given by D matrix. So you see in the pictures on top, the three scales that we analyzed: large, medium, and small tiles. So as an example, you can see the vertical displacement. The first on the left is the discrete abacus model. So the particles are rigid. Rigid means very high elastic modulus compared to the stiffnesses. In the center, you have Kosura, and on the right, you have Cauchy. And as you can see, yes, Cauchy is slightly different from Kosura, but they are very similar. Okay, and this, we expect that. If we reduce the scale, effect changes. I'm just changing the slide. And as you see, the models are very close to each other. Perhaps the Kosura model, for small tiles just shows a different redistribution of the displacement field compared to the Cauchy, which is more concentrated where you are applying the load. This is, of course, half of the model. Okay, we have plane of symmetry here, and the load is applied at the center of the panel. Regarding the horizontal displacement, now we are forced to model the whole panel because the simulation is not symmetric anymore. So the load is basically here, left, discrete Kosura and Cauchy. Here for the horizontal load, you see more difference with respect to the vertical one, because an horizontal load generates more shear effect. So, and remember that, we have this kind of non-symmetry of shear for Kosura. Also changing scale. The effect is slightly different, but very close. Let's go to the hourglass shape. So now we have an auxetic behavior. Auxetic behavior, as you see, we have negative contraction, so auxetic effect, but also orthotropic behavior because direction 1 and 2 are different. This is due to the shape of the tile, because in this direction, shape is narrow, and on the other way is larger. Different scale, and also scale effect due to D matrix, and uncoupled behavior, as we already mentioned. Results. Now we see a difference, more remarked difference. You see clearly that the discrete model is closer to our Kosura continuum model. Once again, this is a continuum model. This is discrete, so made of several particles and springs. This is standard Cauchy. You see the difference in the displacement map. As we change scale, the difference remains. Okay, so this is closer to our model. Horizontal, the difference is more remarked also. You see, our Kosura model is closer to the discrete one. Instead, Cauchy has smaller displacements, as expected. Finally, we have the asymmetric shape, which has a chiral behavior. Chiral because we have a coupled constitutive matrix. We have no contraction, basically because we selected these two edges with the same angle. So, the two contributions, this and that, they cancel out. We also have scale effect, and we also have orthotropy due to the shape, in X and Y. Results. Once again, Kosura and discrete, they are very close. And Cauchy is more rigid. Horizontal, same things. Okay, what about dynamics? We perform the same analysis, so same idea. 3 geometries, different scales. You see 1, 0, 5, 0, 25, so large, medium, and small. For the same microstructures, you have data here for the area and moment of inertia. We need that for the dynamics, okay, right? And we're going to see the first three mode shapes for the three geometries, comparing discrete, Kosura, and Cauchy. Same panel, same rectangular panel. So this is the first mode shape, the second and the third. So we said the orthotetragonal behavior is very close and behaves quite similar to the Cauchy one. In fact, the three modes are very similar, also to the discrete one. The error is also very small, okay, except this one for the third mode, but the others are, let's say, very close to discrete. Let's go to the auxetic. If we have auxetic, and this is, large tiles, you see clearly that for mode 2 is different. Mode 1 is closer. We have this kind of, map. Here, the map is closer to discrete, of course, but here you see more clearly. Okay. So these two are bending modes, and this is axial mode. But look at the errors. The error for our Kosura model is limited, below 5%, okay, except this one. Huh? The error for Cauchy goes from, 30, 46%. That's quite wrong, except for the axial mode. The axial mode works very well. For the chiral is even worse, okay? Second mode, quite good. This is completely different. And this is closer, and this is another story. Once again, the error, very small. The error, quite large. Be careful because this error is very small, but the mode shape is another mode shape. So basically, if you just look at the vibration mode, you can say, okay, the result is good. Yeah, but the mode shape is completely different. Okay, so the result is wrong. So you heard about this many times during the course. So what is the best RVE? Okay, why we selected this kind of RVE? Technically, you should do some tests before, and we did. And you see here a comparison, a table in which we are comparing the solution in terms of work, so energy, for 7 blocks RVE and 4 blocks RVE. So the energy that we are able to compute after the static analysis gives an error roughly of 10–15% compared to the discrete abacus model with 7 blocks. With 4 blocks, the error goes up to 30–40%. So technically, this is much better. So demonstrated by this kind of test that we performed. We also did simulations with 4 blocks, but of course the results are not as good as the ones with 7 blocks. Okay, I want to go straight to the last part, also because we are running out of time. I want to show you some recent applications we are doing with the delatency effect. I should, talk a lot about delatency, but we don't have so much time. Just to say a few words, there are several models available in the literature. Basically, we are assuming that the interface is planar between the 2 blocks, but the interface is microscopically rough. So you might have, some small zigzags or some small, like concrete interface when you have cracking in concrete, okay? Just to have an idea. So you can, of course, you can use this kind of model, which is, uses a simple function or just continuous modeling with density functions. And in the following, I will show you some results regarding continuous density function, which is the one depicted on this figure. How can you interpret this kind of lines? Basically, okay, this means that you have to go up because this is 1 and this is 5. So it is 5 times up, okay? This is the density function. So this is how many of these angles appear in the interface. let's go back. You have these thetas, okay? So how many theta equals 0? In this function, a lot. Okay. How many angles of 45 degrees? Here, 0. Here, 45 is here, you have this quantity in, statistically speaking, you have that quantity of 45 degrees in the micro roughness. So these functions are governed by, these, of course, cosine functions. You can check our work in composite structures for the formulations. Basically, you go to, you're able to calculate the equivalent stiffnesses that we need, which are normal, shear, and the latency stiffnesses. Of course, as we expected, omega-1 function, which is the one, with the peak, which means basically a smooth surface, has the latency very, very small, because the roughness is very small. But omega-5, which is this, which has angles between minus 90 degrees to 90 degrees, has the highest value of the latency. The drawback of this method that we are using is that it's not able, you're not able to have zero delatency effect in the surface, because you're always going to have some, very small angle. Instead, if you use this other implementation, you can get the latency 0 just by setting the angle equal 0. So the surface becomes smooth. Okay, so let's have a look at the homogenization. So what happens when you homogenize, as we did before? This is the same, say, constitutive matrix, but in table form. You have the A terms and the D terms for the 3 scales and the 5 functions. Okay. Okay, so of course we have, scale effect, and we have also the latency. Just to recall you, this is the term between sigma 1,1 and epsilon 1,1. This is Poisson effect, A11 to 2. This relates normal stress and one of the 2 shears, which is sigma 1,2. And this is sigma 1,1 that, sorry, not sigma 1,2, epsilon 1,2. And this is between sigma 1,1 and epsilon 2,1. So you see that the 2 values are different. Okay. All right. This was for the orthotetragonal. This is the same for the auxetic. And this is for the chiral. For the chiral, since we have also B matrix depends on the scale as well as D. So we have, a lot of values, but less values for A, because remember that we don't have any contraction effect for chiral, for this kind of, let's say, shape. No Poisson effect. So of course the terms equal 0, we did not report it. As I already mentioned, we can go from micropolar to Cauchy, and we can notice an interesting stuff is that when you take the orthotetragonal shape and you go from micropolar to Cauchy, you don't have any delatency because of the symmetry. Everything cancels out. Instead, the other shapes, they have delatency effect. I mean, with delatency effect, I mean connection between normal and shear, which we didn't have before. Okay. Okay, this is the geometry we are analyzing. It's a slope. Basically, we have clumped edge here, symmetry here, load applied on a limited area. And these are the results. The results show, of course, for regular shape, which is orthotetragonal, the results between micropolar and Cauchy, basically the same. Okay. And the change, with the delatency, of course, no change. Cauchy has no delatency effect. Okay. So the change is very, very small. In terms of displacements, stress, you see, maps are very, very close. Relative rotation, is a very important kinematic measure for micropolar. Basically, is the difference between micro, so small rotation, and large macro rotation, the rotation that you have in Cauchy also. Of course, it does not appear for Cauchy here because in Cauchy is completely equal zero, does not exist. Okay, but you see from the result here that the values are very nearly to zero. We expected this. Kosura tetragonal very close to Cauchy, so that's correct. So what about tangential strain? You see on the left, epsilon 1, 2, on the right, epsilon 2, 1. Of course, Cauchy is the same, symmetry by assumption, okay? Kosura should be different, but, oh, sorry, but basically it is not. Why? Because relative rotation is almost zero. Okay, so this proves the quality of our solution. Let's go to the hourglass. So the hourglass, in the hourglass, you can start see some effects due to the latency, and of course due to the fact that we have a micropolar, strong micropolar effect, especially vertical stress relatively. But look at the relative rotation. Relative rotation is clearly not zero. Where you go to apply the load. Okay, so close to the load, you have high relative rotation. And this appears also in the tangential strain. So look, left, epsilon 1, 2. On the right, you have epsilon 2, 1. Of course, epsilon 2, 1 is larger due to the vertical load. And Cauchy, which has symmetric strain, does not see this effect because Cauchy is basically the average between this and that. Asymmetric shape. So the 5D latency functions, a little bit of a difference. Here you see, yes, there's a small difference. And also here, relative rotation, we have an effect here on top, of course, larger for large tiles. Smaller for small tiles, because as we go to small tiles, we go closer to Cauchy behavior. Once again, the tangential strain is definitely not symmetric. If you look here and here, you see clearly two different results. And then I want to finish with, say, a new topic that we are trying to investigate, which is the void effect. So with the same geometric shapes, hexagonal materials, we're introducing voids. So we started with this example. This is from, this picture is from the literature. Basically, you take the orthotetragonal regular hexagon shape RVE, and you tilt the hexagons, every hexagon of an angle beta. So by rotating the hexagons, some voids appear. As you rotate, more void you have. Okay. So this is from the literature. This is our picture from the homogenization procedure. So we start compare, some results. This investigation is still ongoing, so I'll just, show you briefly, some ideas. Below, you see the analytical solution. So according to the paper that we are taking, this matrix should be, with the two values equal, as you see. But our homogenization procedure gives different results. Okay. Actually, this is, in my opinion, more correct because this means that micro rotation, according to one direction and the other, they should be the same, but it is not, because if I draw a line here and I look at x-axis or y-axis, the components in terms of the faces that where I have stiffnesses is different. On this side, x, I have 3, and on this side, y, I have 2. It cannot be the same, okay? So of course, very close, but not the same. So this is a justification. And also we are start comparing some, simple results. This is the same panel you saw before, rectangular panel with horizontal load, according to reference and our model with two different values for D11 and D22. Results are very close, so perhaps this difference is not remarkable for hexagonal shapes, regular hexagonal shapes. The same can be said for the relative rotation, which is pretty similar. Regarding shear strain, epsilon 1,2 and 2,1, once again, I want to remark the fact that since we have a micropolar theory, we are able to see this, to see that epsilon 1,2 and 2,1 different. In a Cauchy model, this is impossible to see. And here you can see slightly differences, but I guess the difference is below 1 or 2%. Okay, so in conclusion, I showed you that micropolar effect changes with scale. You see, changing the scale of the tiles changes the result. We discussed, results for regular hourglass and asymmetric hexagonal patterns, which are orthotetragonal, auxetic, and chiral. Chiral, once again, means matrix B, which couples normal and shear stresses and curvatures and microcouples and normal and shear strains. We observe percolation of stress using micropolar theory. This was also observed by others in the literature. Of course, large tiles redistribute stress more due to the fact that we have large blocks in the model. Small tiles should behave like Cauchy, but they are not, due to the fact that we have asymmetric stress. So very close to Cauchy, but not the same. And of course, at the end, orthotetragonal pattern is very close to the standard Cauchy modeling. So I'm open for questions, and I thank you all for your attention. Thank you. I think 2 questions are here.
Thanks a lot.
Okay.
Ok, togliamo lo schermo. Okay, I think that you can ask the talk of Dr. Fantuzzi and Professor Pau are now open for a short discussion before going to the last talk of today. Razi, please.
Hello, dear professor. Could you hear me?
Microphone.
Could you hear me?
No.
Now?
I think the others in the room can hear me.
Yes, we can hear you.
Okay, thank you.
Please, Razi, ask.
Okay, sure. I had a question about the composite with microcracked matrix. Okay, I don't understand. Why do we always say that the particles should be rigid in the model? I mean, if you want to consider flexible particles, where should we upgrade the model to account for flexibility? I'm sorry, your microphone is off. The microphone.
Okay, yes. The deformability is concentrated in joints. Joints are the part which deforms. And moreover, I have to add that I gave a general picture, but actually in the model, there are no particles, there are only pores. That's a particular case of the more general model of composite materials with microcracks. Okay. Yes. Okay.
So you mean that, for example, if you want to consider the particles, we can just consider the flexibility in the particle itself. We cannot consider the flexibility interaction with the matrix. You know, it's just
I am not sure I understood your question. In this model made of particles, generally particles have a higher stiffness than the matrix. Then most of the deformability is concentrated in the matrix. And that's that part which gives the stiffness, which is then included in the constitutive constants of the different stresses. But if you're interested in that, there is a paper we have just published in Mechanics of Materials. Therefore, you can give it a look at the give a look at the details in here, because there is also some mechanical analogy for like springs, which connects these particles, which is quite easy to also visually understand. Therefore, yeah, better than, yeah, I think that's that you can give a look at that paper, because there's an explanation of that.
May I add an observation? I want to take the occasion to remember of my last lesson of yesterday. I introduced different approaches for homogenized materials, and I distinguish it between materials in which we have a low volume fraction and essentially deterministic distribution, in which the particles are much more rigid than the medium in which they are embedded. And another approach that I also show, and today Dr. Tipellis deepened it in his in her lecture, was materials with dilute concentration of also deformable particles. So the procedure that Professor Pau adopted, we worked together at this, consider the Cauchy-Born homogenization procedure that I explained in the previous lecture. But in the case of materials, and then I will send you, of course, or the PDF of the lecture, the deformability of the grains in polycrystalline materials, for instance, is accounted for as deformability equivalent, energetically equivalent stiffness at the joints, as in the homogenization path, at the end, you have to consider an average deformability of the whole. And in a smeared sense, this was the approximation that we adopted. Of course, if you want to take into account directly the deformability of the bodies, it is better to follow other procedure in which you don't assign a rule, a kinematical rule that we call the Cauchy-Born rule, that was also a Foyt generalized rule, but use the procedure that Dr. Tipellis explained to you, that is the solution of specific boundary value problems of Dirichlet or Neumann type. And in that case, you can include directly the deformability both of the matrix and of the particles, because you are dealing with the two-phase materials. In the former case, the particles are rigid, are conceived as molecules of the molecular theory of elasticity, but that are particles inside which no forces are accounted for, and in particles that interact with the other through forces coupled and other additional forces that we call the configurational forces and so on. There are a different kind of approach to different kind of composite materials.
Mm-hmm. Thank you so much. It was really clarifying. Thank you.
And to Nicola, to Dr. Fantuzzi, do he have some questions? You are tired, I understand. But of course, if you want to ask for something after looking at the material that I will distribute to you, you can do using the email of all the lecturers of this course. So you have time to check and verify if you need some further explanations or further materials and papers and so on. Okay, what do you think? We can do a very short break and start the last talk at 15 minutes past 5. Hmm?
Okay.
Dica. Ci sta raccontando tutti i fatti suoi. È iniziata la registrazione?
Sì.
Okay. So, we are at the end of the session, and the last seminar, last talk is given by Dr. Marco Pingaro. And Marco Pingaro has get the master's degree at the University of Pavia and also the PhD degree at the School of Advanced Studies of IUSS of Pavia. And he is now assistant professor at the Department of Structural and Geotechnical Engineering in Sapienza. And his main interest in research are devoted to computational mechanics and advanced numerical tools, to which he also dedicates this lecture, in particular the so-called virtual element methods, of which he will speak right now, and many other computational advanced methods as mixed finite element and so on. And please, Marco, thank you for accepting this invitation and for giving this talk.
Sure. Screen.
Okay, thank you so much for the introduction, Professor Paolucci, and for giving me the opportunity to speak today in this course. My talk is a sort of extension of the topics covered in the lecture of the Professor Paolucci and Dr. Maria Vallebellis. In particular, I would like to show you the work carried out during this year within the Professor Paolucci and her research group on the homogenization of random composite material. Okay, this is the outline of the presentation that is simply structured in 4 main parts. Short motivation of the work will be given. After that, I will give a brief recall of the homogenization strategies for random composite material and its integration in a code totally in-house implemented at Sapienza University. Then some results obtained using the code and some final remarks and future development will be shown. As Professor Paolucci and Maria said, a large range of material used in different engineering applications, mechanical space, or industrial application in general, exhibit a random structure with random inclusion dispersed in a matrix. And some examples are here reported in this slide, and they include classical materials such as concrete, porous rock, and or masonry, or advanced material like metallic form, ceramic metal matrix composite, polycrystal materials, and so on. Study this type of material is an open challenge for the complex behavior and for the interesting mechanical, thermomechanical, and acoustic characteristics. And homogenization technique is one of the best strategies useful for study this type of material. So we can start with the first part of the presentation that is focusing attention on the homogenization process for random material. First, I want to recall that in the context of composite material, homogenization are successfully adopted by several authors for classical and enriched continuum. And the synthetic literature is here reported, not exhaustive, but what are the objects of the homogenization? The object of the homogenization, as you can see in the previous lecture, are the estimation of the homogenized elastic moduli and determination of the representative volume, the RVE, that do not priori define in the case of random materials in which it's not possible to identify a repetitive cell. Regarding the model, we consider 3 different types of 2D models in which the material is modeled as a bimaterial system and all components are considered linear elastic at this stage. The first model takes inspiration from the work developed by Professor Paolucci, Professor Stoia, and Maya Laura, and here reported. In this case, we have circular inclusion dispersed in a matrix, and 2 main cases are considered depending on the stiffness of the inclusion respect to the matrix. The 2 cases are here reported, and they are stiff inclusions in a soft matrix or soft inclusion in hard matrix. I have used white color for identify the soft part and the black color for the stiff part. Furthermore, we consider as a deterministic parameter the average density of the medium that is defined as the ratio between the area of the inclusion and the total area of the window considered. The shape of the occlusion, in this case, circular, and the dimension is fixed by fixing the diameter of the inclusion. Moreover, we fix the minimum distance between the inclusion, the so-called hard core distance, measured to 0. In this way, no compenetrating occur between the inclusion. Okay, the compenetration is not are not acceptable. Okay, and finally, the mechanical properties of the inclusion and the matrix. Regarding the random parameter, they are the number and the position of the inclusion. And I want to notice that it's important to take account the possibility of the inclusion cutting the window edges in order to not obtain wrong result, as Professor Tovalucci underlined in one of her work. In the second step, the procedure has been improved in order to take account polycrystal material within or zero interfaces. In the left part is reported the model with the interfaces, and in the right part of the slide is reported the model adopted for the CMC material. In the first case, the deterministic parameters are the average dimension of the grains, the thickness of the interfaces, and the mechanical properties of the materials. And in the second case, the deterministic parameters are the average dimension of the grain, the average density of the different phases, and the mechanical parameter of the single phases. For both type of model, the random parameters are the position and the shape of the grains. And for both type of models, the grains are modeled as a polygonal element of random shape. For all model, the circular particle inclusion and grains, the deterministic parameters play the role of the input for the homogenization procedure. So now I want to describe step by step the statistical homogenization procedure necessary for random materials, as explained by Maria Laura this morning. It's possible to summarize the procedure in 5 or 6 steps, depends on the model adopted. And the first step, we set all deterministic parameters previously shown for the different model, and we can choose a trial dimension of the window size L. And after that, it's possible to define the normalized window dimension delta. The normalized window dimension is the ratio between the window dimension and the diameter of the inclusion, or the average dimension of the grains. As the second step, we determine the expected number of inclusions for grains in each trial window using a Poisson distribution. After that, in step 3, for all realization, we randomly generate the position of the inclusion and the shape in the case of grains material. In this last case, a random Voronoi tessellation has been adopted. These strategies correspond to the so-called moving window technique, and the idea of the moving window technique is to move within the material and take a snapshot as depicted in these two figures. After that, at step 4, we apply over all cells Neumann and Dirichlet boundary condition, and we solve all boundary value problem. In the 2D cases, we apply 3 boundary conditions for the Dirichlet and other 3 boundary conditions for the Neumann. So for each realization, we have 6 boundary value problem to solve. After that, we compute the relative homogenized constitutive parameter using the Hillman condition explained by Maria Laura this morning in her lecture. After that, we repeat the step 2 to 4 by increasing the window size L. The procedure stops when we reach the convergence, and typically we obtain a similar result sketched in this figure, where the Dirichlet and Newman boundary value problems define the upper and the lower bound solution, respectively. A statistical criterion is adopted for stop the procedure when the number of simulations necessary to obtain the average of the elastic coefficient that do not differ of a given tolerance. And that's depending on the data dispersion. I just want to notice that the adopted convergence criterion is valid for any value of material contrast. Material constant is defined by the ratio of the Young modulus of the inclusion and the Young modulus of the matrix, or the ratio between the Young modulus of the 2 phases of the composite material. The procedure illustrated have an high computational cost and do not permit to perform a series of parametric analysis. And for this reason, the procedure has been automatized in code totally in-house implemented, the so-called fast statistical homogenization procedure, FSHP. And by using FSHP, in fact, the procedure rapidly converges and permits to analyze and perform easily a lot of analysis. Currently, the procedure permits to adopt 3 types of models as shown in the previously slide: circular inclusion, dispersion matrix, and polycrystal material with thin or 0 interfaces. The code, FSP, the code is a kind of macro code using other codes directly in-house implemented, such as PVM, PVM for solving the boundary value problem, and PVM is a code developed at Sapienza University that uses the virtual element method. And the other main programs are the ParaView for showing the results of the analysis. And ParaView is a data analysis and visualization application. Triangle is a software developed at the University of Berkeley, and it's used for meshing the matrix part or the interfaces between the grains. And Polymesh developed by Professor Champagne for generating the Voronoi tessellation. As an example, in this slide, in the left part of the slide, we can see an example of the input file for FSP, and it's written in XML format. As I said, in the case of grain inclusions, we adopt Polymesher as a tool for meshing the geometry. The strategy for thin interfaces is here reported, and we generate an initial Voronoi tessellation by using a polymesh. After that, by a shifting procedure, the interfaces between the grains can be created. And finally, using triangle, the computational mesh has been obtained. In the case of zero thickness interface, the procedure stops at the first step. Okay, in order to reduce the computational cost, the virtual element method has been adopted. Virtual element method, what is the virtual element method? That is an extension of the finite element method, and whose characteristics are useful for a large range of engineering application. I just want to highlight the future that will be used in this work without focusing the attention on the method. And certainly the first one is the possibility of dealing with a very general polygonal elements of any shape. The computation of the stiffness matrix is fast and easy because you don't use Gauss point for the integration, and we don't use, it's not necessary to compute the shape function. Furthermore, other features are the possibility to use Ingegneria easily, and this is very useful for local mesh refinement. And the possibility to coupling FEM and VEM, and this is possible because the VEM has the same boundary degrees of freedom, the same boundary degrees of freedom of the FEM. This feature have been used for creating a specific and ad hoc mesh in order to increase the velocity of the procedure. And in particular for all types of model implemented in FSP, we adopt a singular element, circular or polyhedral, for the inclusion, and triangular elements for the matrix part or for the interfaces. In the case of circular particle, the mesh is fine near the inclusions and coarse elsewhere for reducing the time consuming. And the time consuming in the case of particle inclusions are here reported in this graph. The graph shown the time analysis in second at varying the window dimension. In blue line, the time consuming of the standard FEM of degree k equal to 1, and in red line, the time consuming of the standard of the VEM of degree k equal to 1. And the maximum reduction in terms of time is more or less for in the cases of the large window is 25%. It's not apparently an analog value, but when we perform 100 of analysis, the reduction in time is consistent. While in the case of polycrystal material, the reduction in terms of degrees of freedom is about 300%. It's a very high value. Moreover, I want to underline that in the case of polycrystal material, with the interfaces, we largely use the opportunity of them to use Eigennodes. Okay, so now I switch to the second part of it. It's more interesting. It's the, the results. I want to show some results obtained by FSP. The first result concerns particle composite. And the first numerical result is a comparison between the previous procedure that used FEM of degree k equal 2 and the new procedure with VEM of k equal to 1. We consider two types of materials, one with stiff inclusion, one with soft inclusion respectively. The mechanical parameters are reported in the table. The two graphs show the homogenized bulk modulus versus the normalized dimension of the window delta. Okay, in red and blue, the results refer to the Dirichlet and Newman boundary condition respectively, and we use the cycle marker. And the cycle marker is adopted for the old procedure and the cross marker for the new procedure. What can you see in this graph? You can see that in the case of soft inclusion, the solution obtained with FSP is in a good agreement with the previous one, but in the case of stiff inclusion, the results of the new procedure don't match very well the result of the old procedure. And this is pretty related to the high gradient concentration of the stress around the inclusion in the case of stiff inclusions. And another interesting result is the possibility to model large window. And this is pretty related to the reduced number of degrees of freedom using the VEM methodology. And this is very important for the material with high or low, very low value of contrast, which request high window dimension for reaching the convergence. And after that, we have performed a series of parametric analysis. We study principally these two main cases, material type A with stiff inclusion, material type B with soft inclusions, the material contrast varying in the range of 10 to 1000 for the material type A and 10 minus 1 to 10 minus 3 for the material of type B. The result obtained for this different level of contrast are reported in the left part in terms of homogenized bulk modulus, normalized with the homogenized bulk modulus at RVE, varying the window dimension. Okay, all bounds tend to get closer to 1. In the right part the minimum number of analyses necessary to reach the convergence at varying the window dimension are shown for the two types of materials. The minimum number of simulations decreases when the dimension of the window increases. And I just want to notice again that using FSP in the case, in this case, we arrive to delta equal to 50, and this is very, very large window. Using the past procedure, it is not possible. In this slide is reported for me, the milestone results of this campaign of parametric analysis. On the left, I reported the dimension of the representative volume element at varying the contrast of the material. When the contrast is equal to 1, the material is homogeneous, and the representative volume element do not exist in the sense that the window, all window are a representative volume element. In the right part, in the right graph, the numeric number of simulation necessary to obtain the convergence at RVE dimension and are reported at varying the contrast. The combination of these two graphs allow us to easily obtain the dimension of the representative volume element and the number of simulations necessary to compute the homogenized elastic moduli without perform the wall procedure. For instance, if you have a material with the contrast of 100, by using the first graph, we can obtain a dimension of the window more or less equal to 31, 32. And by using the other graph, the minimum number of simulation necessary to reach the convergence is more or less 21. In this way, you must perform only 21 analyses with a fixed dimension of the window in order to obtain the homogenized elastic model. The next application is related to the porous media. As I shown in the comparison between the standard procedure and the FSP, VEMOD VK1 provide reliable results for material with low contrast. And for this reason, we decide to perform a study for porous media. We perform two different studies. The first one, in the first one, we identify for an eigenvalue of porosity of the media, the representative volume element, and its homogenized mechanical properties. And the second one, exploiting the opportunity provided by FSP, several parametric analyses are performed by varying the porosity in the range 5 to 40 to investigate how the RVE changes in relation of porosity and to evaluate the sensitivity to the porosity. The adopted properties, mechanical properties for this study are here reported in the table, in the top right of this slide. Starting from the first study, in this slide is reported the value of the normalized bulk modulus versus the window dimension. At the window dimension increases, the two bounds relative to the Dirichlet and normal boundary condition tends to get closer, but even if there is a mismatch, because the two bounds became quite parallel, the difference in terms of converse trend depends on the data dispersion of the results. And in the left part, the two small graphs shown the normalized average bulk modulus for the Dirichlet normal boundary condition versus the number of simulations for different window dimensions. And in the right part of the slide is reported the coefficient of variation at varying the window dimension. Okay, in this slide is reported the minimum number of simulations required to for reaching the convergence at varying the window dimension. Red line, the clear boundary condition, and blue line, the normal boundary condition. The two bounds tend to decrease. They tend to the same value when the window dimension is increased. After that, we studied the sensitivity to the porosity. We analyzed different level of porosity, starting from 5% to 40%. As intuitable, the homogenized moduli decreases when the porosity increases, such as the bulk modulus here reported. While the homogenized Poisson coefficient has a particular behavior, it decreases at increasing the porosity, but the two bounds are exchanged. The Newman boundary condition is the upper bound, and the Dirichlet boundary condition is the lower bound of the solution. In black line is reported the average value of the two bounds. Concerning the dimension of the representative volume element, the V, respect to the porosity, it linearly increases when the porosity increases. And when the porosity arrives to 20%, the RVE decreases. And after that, after 25%, the dimension of the window side dimension of the RV remains quite constant. What is the motivation of this behavior? The question is why after 25% of porosity, the RV remains quite constant. Because the randomicity decreases in the sense that when you increase the porosity over a given limit, the possible position of the inclusions decreases. And the material tends to be a fixed structure. Okay, and in the right part of the slide, the coefficient of variation at varying the window dimension are reported, but they are not very interesting. Now I switch to the other type of model. Now I want to present some results obtained applying the statistical homologizations to polycrystal materials with thin interfaces. And as suggested by many authors, polycrystal materials are characterized by polygonal inclusion grains with thin or thick interfaces, different level of porosity. The porosity is here schematized using the white point, or characterized by one or two end phases. And in this study now, I want to focus the attention on the thin interfaces polycrystalline material. The first result is a comparison between the proposed procedure using VAM, in which that I remember that all grains are modeled with a single element, and the standard procedure with FEM assumed as a reference solution. This in order to check the reliability of the procedure. For this test, we assume fixed geometry, and in the two tables are reported the homogenized elastic moduli for different level of contrast. As you can see, but probably the table is very, very small, but the what can you see in these two tables? That the maximum error for the highest contrast is equal to 0, is close to 0.1. It's very, very, very low. And this shown the wellness of the procedure. After that, we consider for contrast, 2 for stiffness grains and 2 for soft grains, respectively, in order to determine the homogenized moduli. And this slide is reported the bulk modulus at varying the window dimension for soft inclusion and the relative coefficient of variation. At the window dimension, the two bounds, the same as a same trend to the porous material tends to get closer, but even if there is a mismatch because they became parallel. And for the stiff inclusion, we obtain the same trend of the soft grains, and in the right part you can see the same, the related coefficient of variation for this case. Okay, and for this is the last one numerical example, and in this case I want to show some result obtained by modeling ceramic matrix composite, in particular the aluminum zirconia CMC material. This work was done in collaboration with Professor Sadowski. Professor Sadowski is a full professor at the University of Lublin. Aluminum zirconia is an interesting material for its useful characteristic, such as lower density and significantly higher resistant to various corrosive factors, including high temperature and abrasion. The model adopted in this case is the two-phase CMC, in which aluminum and zirconia play the role of two phases. The mechanical properties of the aluminum zirconia and aluminum and zirconia adopted are here reported in the top left of the slide, and we consider 5 nanometers as an average dimension of the grains, and 4 level of percentage of alumina be considered in the range of 20 to 80%. In the two graphs I reported the homogenized bulk model as varying the window dimension delta for Newman and Newman boundary condition in the left part, and the Dirichlet boundary condition in the right part of the slide. The homogenized bulk modulus remains constant at varying the window dimension, and the two bounds relative to the Neumann and Dirichlet boundary conditions are quite close. This is because the contrast of the material is very low. So the constant in this case is the ratio between the Young modulus of the alumina and the Young modulus of the zirconia is equal to 2. It's very, very low value of contrast. But the coefficient of variation for the different level of alumina here reported give an idea of the convergence trend. Increasing the window dimension, the coefficient of variation decreases, and to bounce relative to the Neumann-Dirac boundary condition tend to be closer, as in the all example, numerical example. But the main goal of this study is here summarized. The graph shown the bulk modulus and the convergence, varying the concentration level of the alumina for Neumann and Dirac boundary condition, respectively. When the percentage of alumina increases, the homogenized bulk modulus increases, and the relation between the homogenized bulk modulus and the percentage of alumina is quite linear for the Dirac boundary condition and non-linear for the Neumann boundary condition. But what is the main result? The result obtained are in well accordance with the rule of mixture, assumed as the reference solution and reported in the right part of the slide. The rule of mixture gives an analytical approximation of the homogenized moduli for the two phases composite, as Marilla was shown in your lecture of yesterday. Furthermore, level of concentration of alumina. Okay, this is very good agreement with the analytical approximation, and this is one of the best result of this last study. So, in order to conclude this presentation, some final remarks are summarizing. The main goal achieved are the total integration of the homogenizing procedure using the VAM methodology, and its extension for taking into account grains inclusion with thin or zero in interfaces and B phases material. The adoption of them of degree k equal to 1 permit a reduction, a very high reduction of the computational burden. And furthermore, the adoption of FSP permit a large scale campaign of analysis for different types of materials, such as material with circular or polygonal inclusion, like polycrystal and CNC. Regarding the future development, are manifold, starting for considering the nonlinear behavior of the grains interface, to use H and Continuum to improve the description at the meso and micro scale, or use high order of VM element to solve the problem related to the stress gradient concentration between rigid inclusion. I conclude. Thank you so much for the attention. This is a short reference area reported, and I want to thanks again all people of the research group. Okay. I'm here.
I have a dream.
Penso che sì,
Okay, thank you, Marco, for this presentation. And yes, the paper is open. The work is open for discussion.
forse perché si è chiusa.
Of course, ma vieni qui così ti ascoltano pure gli altri.
Zoom. Ecco.
No, rimetti la presentazione.
Ah, ok.
Rete un po' difettosa.
Schermo 2, but if you want, I use this. Okay, I stop the. Oh, no, aspetta.
Periodo di negatività.
Così la guardiamo qua, la guardano anche loro un attimo. Sorry.
Fai duplica.
Sì. Questi schermi. Wait.
Yes.
And
share screen.
I share the screen this way. Okay, this one. I think
Okay. Go back. The last slide before the conclusion.
This one.
This. Okay, this is very interesting. Actually, was the first question when you started. This was my question, number one. But you answered the question. Comparison with rule of mixture. The second question is, did you do it for voids? Rule of mixture, but not for two materials with voids. There are several homogenization procedures, continuum with voids, different distributions. This is linear.
Yeah.
There are several, like parabolic or.
okay.
So I think you can do the same. Instead with composite with two materials, but material with voids, porosity.
Okay. Thank you for the suggestion.
Second point, you showed a picture. Go back.
Ma for polycrystal within.
Wait, you showed the picture. No, back again. No. I tell you the story. You showed the picture where you compared two. It was not a comparison. Where you showed two pictures where there was a minimum for the same modulus of elasticity of inclusions and matrix. And there were a number of simulations.
This one?
Yes, that one. Okay,
Okay.
I just wanted to know how you measure this delta RDE.
Delta is the size.
size
Is the window dimension.
It
Probably it's not very clear, this graph, in the sense that for contrast equal to 0, you have the material is homogeneous.
Yeah, that's fine. No, I got the abscissa. I don't understand the ordinate. What does that 40 mean?
Okay, because it's the normalized window dimension. It's the ratio between the window dimension and the dimension of the inclusion,
the size of
the diameter, or for polycrystal material, because at a different size, you assume an average dimension to define delta. Okay. And so for homogenized material, the number of simulation is equal to 1. Qua mi sa, questo qua piccolino. Sì? Ok, perché ho su tutti. L'altro? Ok. Close the. Click here. Okay. Okay.
Okay. Are there any other questions? Are you still alive?
Yes, we are. Yes, we are. Thank you so much for the great presentation.
Sorry, Adi.
I thank you for the great presentation. Thank you.
Thank you, Adi.
Okay. If there are no questions, I just want to go to close this course, hoping that to have offered a wide variety of approaches concerning the multi-scale modeling in composites and in general complex materials, and with the different languages and different kind of deepenings on continuum mechanics foundations and mathematical and numerical foundations, and also computational aspects. And I hope that the seminars of today, after the lectures, helps in focusing. No, si sente tutto, ragazzi? Scusate, Marco. Helps in focusing the possibility of applications of this kind of different procedure of multi-scale modeling. And I will send you, Andrea, is Dr. Arena that is connected online, will contact you and give Andrea,
yes.
Correggimi se sono in errore, if I am wrong, but we will send a link to a drive folder where you can find all the presentations of the course and some selected papers that helps in the studying of the content of the lessons. And if you need to contact any of our lecturers, of course you can. And I hope that this overview stimulate and favorite your future research work. Vuoi aggiungere qualcosa, Andrea?
No, simply if some of them need a certificate, you know, an attendance certificate.
Okay.
Yes. Just contact us and we will check the presence, of course, through Zoom, and then we'll provide the certificate of attendance.
Okay, yes, we will send you the certificate of attendance because we registered your participation both online and in the presence.